Lahiri has presented and published more than 80 research papers in the area of artificial intelligent neurorehabilitation techniques, non-invasive physiology-based diagnostic screening techniques, effective computing, virtual reality-based physiology-assisted skill training platforms. She has completed more than 4 research projects and has published a book on computation view of autism. Ma'am, we are very delighted to have you here on this online platform to share your work. Let us know you. Start the session. Over to you, ma'am. You can start.
Okay, thank you. Thank you so much. Good afternoon to all. Let me just open my screen and so am I audible and the slides are visible?
Yes, ma'am. It is
Okay,
visible.
okay, okay. Okay, thank you for the invitation. Myself, Uttama Lahiri from IIT Gandhinagar. Ma'am has given a good introduction about me. So today I'll be speaking on artificial intelligence enabled healthcare technologies for diagnosis and rehabilitation. Um, uh, Ma'am has already told about me, but I felt it would be nice if I can give uh, maybe a minute for presenting where do I come from and what is I have been doing um, last few several years. So I did my BTech from Jadavpur University, Calcutta, and then I was in the electricity distribution sector, working in industry for quite some time, um, and um, and then I went for my masters at IIT Kharagpur in instrumentation engineering, followed by a brief tenure in at Tata Steel in the automotive sector, mostly in the R&D. I have been working, and then I went for my PhD at Vanderbilt University. After completing my PhD, I was in a postdoctoral role where I have worked at the pharmaceutical sectors in US in an industrial setting, and then I came to the academia. So though I tell that I have come academia after a long journey, but you can see that everywhere it was sort of I was learning, I was checking it in real life, and then again going back, learning, and again seeing my concepts in sort of real practical scenarios. All along, I have been working with signals, and obviously, I have been working with automation a lot. So mostly I work with intelligent systems while I work with different gadgets and different sensing mechanisms, eye tracking, biofeedback. I do a lot of sensory fusion. I apply sensor signal processing, data mining techniques. I use a lot of machine learning in my work. And my research is mostly in the two sections, which is adaptive human-computer interaction, mostly in affective computing, and the other is adaptive human-computer interaction in rehabilitation. So today I'll be speaking on the second arm of my research, that is in rehabilitation. So today I'll be covering two of the many screening techniques that I use, two screening techniques for neurological disorders and one rehab, again for neurological disorders. So first one is the gaze-based. So when I say gaze-based, what does my eye tell about my, does it give any signature of my neurological disorder? So that is the question which I started with. And you know that I apply this for post-stroke patients, and all of you, most of you might know that it is a very common cause of death, and also it leads to disability, where my next part of the talk will be on rehabilitation. And quite a large number of people become affected with stroke, but about 25% do not survive, but the rest 75% stay with disabilities. And of those who stay with, who survive, 86% of them show oculomotor problems, that is in eye motion. Either it is in fixation, that is in ocular position, or in moving the eyes, that is exhibiting smooth pursuit. So when I see a plane moving on the sky, my eyes go on tracking the plane, and that is what is smooth pursuit. But if there is a beautiful flower in front of me and I fixate on that flower, then that is what is fixation. So here I'll be working on these two aspects uh, of the of the vision. Now, and as you might know that, so the question comes, okay, eyes and stroke, where is the linkage? So our brain is the linkage, our cerebral cortex, which is again connected to the brainstem. So way down, I don't know whether you can see my cursor. So way down is the brainstem, and the brainstem in fact controls different muscles. But here I am more interested into the oculomotor muscles, which is the superior rectus, inferior rectus, which makes the vertical movement of the eyes up and down, and then is the lateral rectus and the medial rectus, which is left and right movement, again based on the lateral movement of the eye, and the other is the torsion, that is rotating eye about a fixed axis, and which is the inferior inferior oblique and the superior oblique muscles. And now all these muscles are connected to specific cranial nerves and the nuclei. So you can see there are oculomotor nuclei, trochlear nuclei, Abducens nuclei, which are actually controlling the eye movement. So any lesion at any portion, either in the supranuclear or the infranuclear portion, affects eye movement. And that is what is the basis of our research. We started from there. So you can see that mostly in frontal lobe. So this is the frontal lobe, the one which is in the front portion. The frontal lobe causes the eye fixation to shift on the ipsilateral. That is, if a person has a right-handed stroke, then the eye gaze will tend to move to the right side, and so the person will tend to miss the left side, that is, which is called as a visual neglect. So there is an eye abnormality. And also there is you will find that generally the smooth pursuit, that is the way I am following a slowly moving target, that also has relation with higher cortical centers. It is very much connected with the cerebellum, which is the below portion which you can see on the brain. It's very much connected, and also even in the frontal eye field and the frontal dorsolateral frontal DPLFC, dorsolateral frontal prefrontal cortex. So these are the areas where, and the frontal stroke is very common in patients. Also the patients exhibit nystagmus, which is sort of rhythmic shaking of eyes. I will show a small video to tell how the eyes wobble.
Hi, my name is Brian Prowl. I'm a physical therapist and I specialize in the treatment of vestibular imbalance
I
disorders.
leave these portions, so this is not that crucial. So you can
Once we
see.
start, you can use your hand or you can use a piece of paper. And what you'll want to do is we'll start with the right side. Put your hand or the paper on the right side and you'll ask the patient to turn their eyes to that left side. And you'll look for the involuntary eye movements in this position.
આપણે છે ને આપણે
After
બીજાને
that,
બીકમાં
you'll
રાખવાના
switch
guys.
to the right
આપણે
side
બે ના
and you'll have the patient move their
આપણે
eyes
કોઈને
to the
આયતા
left.
નથી પણ બે ના માંગતા
Those involuntary eye
જો કે
movements.
આમાં તો પબ્લિક ડાઉટ કરે જો કે
Madam, we
જ્યારે આપણે
cannot
જાણે
see the
નથી ના
video.
First type of
You
involuntary
cannot?
આપણે
movement you might
તો
see
અહીંયા
is
ડાઉટ
the
કરે
eyes shaking from
Okay.
side to side.
No, ma'am. Audio is coming.
Side to side.
Someone told me the video was coming.
Similar to the previous type, you may also notice an eye movement.
So
You have to share that screen of video.
I am doing that because there is an online link here. I have connected that link. So do you want me to?
You have
Uh,
to share the whole desktop, then only we will be able to
I have done
see.
that. Okay,
Okay,
let me do it once again.
thank you.
I just log out. I just open share tray, and there it gives. Okay, I have done PowerPoint. So you are telling that. Um,
to share the
Shared
whole
screen.
desktop.
Share screen.
Yeah. Yeah,
Okay.
select the whole desktop. Yes.
Okay. And just once again, I don't remember whether I have. Are you able to see it?
Yes.
Okay. So let me know if you can hear it. Can you hear?
No, audio is not available.
Okay.
Video is available. You have to connect
Okay.
with the computer audio when it is
I
playing.
think so. I have done it. Let
You have
me.
to again turn that button on for audio from computer
Yes, I
for
have
that
done that.
particular share.
I have tried to do that. Maybe okay, I forgot. I failed. Maybe I have forgot. Okay. So can you? I hope this time it will work.
Hi, my name is Brian Prowlin.
Okay.
What you want to do is you want to turn their eyes to that left side, and you'll look for the involuntary eye movements in this position. After that, you'll switch to the right side, and you'll have the patient move their eyes to the right. And again, for those
Ma'am, the
involuntary.
video is not visible.
The first type of
Still, it's not
involuntary eye
visible.
movement you want to see is eyes shaking from
No, it
side to
is
side.
visible.
You
Is
travel
It's
visible.
a
from one
visible.
side, then to the other,
Is
then
visible.
to the other.
Visible.
It's visible.
Similar to the previous type,
And you
you
can
may
hear as
also
well.
notice an eye movement that moves
Yes,
side to
ma'am.
side,
Okay.
but at the same speed when looking left and right. Another type of eye movement to look out for is any up or down eye movement. Finally, you might see a type of eye movement in which the eyes just seem to rotate or turn in place.
So why I gave that brief video to tell that the process of finding the problem in one's eye movement is so tedious. So the literally you need a therapist to go to the patient and do these processes to find out these eye movements. And we were showing enlarged view, but actually these movements are very minor. And technically intensive eye tracking based system or a camera based system would be needed to pick up one's eye movement. And that is what we have done in our research. Here is what the therapist does. So the therapist uses something called as an optokinetic drum, and the therapist actually rotates that drum at a very low speed and asks the participant to or the patient to look towards the drum. And if the patient's eyes wobble, like the where you have seen in the video just a few minutes back, then that is where the patient, the therapist understands that, or the clinician understands that there is a problem, and then he goes and tells, okay, why not you use an MRI to find out where's the issue, and then the stroke is being detected. So it is a very tedious process, and also it is actually very subjective, because if the therapist or the specialist misses the eye movement, then he tells the patient to go back to his house and nothing has happened. It is very often to go for errors. Also, there are different tests which are called as head impulse nystagmus test of skew, where there are different therapist-led tests which are very strenuous and which are very time-consuming and also costly. So that was sort of our motivation, where we went for a quantitative oculomotor assessment tool for neurological screening. Um, so we mostly worked on three different aspects, which is eye fixation, how I fixate my eyes, how I move my eyes slowly following a target, and how I blink. Because literature shows that if the patients have stroke, then their blinking rate reduces, and that is something called as a dry eye effect, because that is where you will find that their eyes tears it sort of tears their eyes, so the tears fall from their eyes because that they have an itchiness because they cannot blink. And so this is a problem. So we wanted to map these to our neurological dysfunction. So before going ahead, I'll tell a small story. So, and one summer I was working with my student, and One of our IIT Gandhinagar members, a very senior person, we tested him with our setup, and he was very fine. He was absolutely fine. And then we could see that our data was showing something different from the normal pattern. So we went to the doctor, our institute doctor, and we asked that we are seeing a difference in the pattern. What is the problem? Is there any symptoms of stroke in this person? And then the doctor said that, okay, about 2 weeks back, none of you knew, at 2 weeks back, there was a mild attack, and very mild attack, and the person is absolutely fine, but he had an attack. And it's nice that your system was so sensitive to pick that up. So even for very mild cases, our gaze-based tool, which has already been applied for patent, can pick up the dysfunction very clearly. And of course, it can also pick up which portion of the brain is having an issue. I'll come to the data, which will be very explicit then. So this is the experimental setup. The participant is sitting in front of a computer and with a stimulus being placed and eye tracking. So you can see eye tracker written, placed on the, let me see if I can use the laser pointer. Yes, the eye tracker is there looking at the person's eyes, and the person is told to put his chin on the chin rest. And this is how we are giving the stimulus. The stimulus is fixated at the center, then slowly moves to the right, comes back, slowly moves to the left, top and bottom. So idea is to find out the smooth pursuit and the fixation during horizontal and vertical movement of the eye. And so we present the virtual reality based task, and this is the task which I was just mentioning. We extract the gaze related data using a C++ application interface which we have developed, and then we process it in real time to give a particular feedback, and the feedback can be based on the user's need and based on the clinician's need. So I'll run a small video. So I'll run a small video. So this is a view of the task, and there is no audio in this. There is only video. So if you don't hear anything, nothing to worry. So this is a small camera system, an infrared camera, where we are first doing the calibration. And then this is the task where it's hardly a 5-minute task. I'm giving a very short presentation of the task. So about 40 seconds of task. You will see the stimulus goes to the right, comes back to the center. Again, the stimulus comes to the left, and that is the portion where it is going through smooth pursuit. There is a fixed speed with which we move based on the therapist's input. And then again, it goes to the north, that is stop, comes back. Again, it goes to the south. So this is the task, and that is repeated over trials. It's a very simple task, but there is a lot of image processing involved. So I will hold on to this. So here you can see, this is the typical stroke case where you can see the deviation in the looking pattern is much more than your case, which is the green case, that is the healthy, and this is for both the left and right eyes separately. So if a subject has issues with the right eye, you can make out that there is a stroke in the left hemisphere of the brain. So that's how it becomes very important. Now, this is how the stimulus we give. So you can see that this is a healthy case. This is the smooth pursuit representation. And this is where you can see that the eyes are literally moving in different directions. And these are the coordinates of the eye. And this is a stroke case. So there is, you can make out the difference, and we give different metrics to identify the extent of stroke. Now, and just feel free to stop me at any point if you have any questions. So what we do, we find out the pupil diameter and we get the gaze coordinates, where the person is looking. We extract both static, that is when the object is fixated, or object is static, that is fixation, and when it is dynamic, that is the smooth pursuit. We do data smoothing, a lot of signal processing is involved in this, and we extract different features. That is how much one is deviating, what is the overall length in the while following the target, what are the frequency domain characteristics, the power spectral density, and also the blink rate and the viewing duration. So we took a study from a civil hospital. We took participants from civil hospital, 8 age-matched healthy and post-stroke patients, and you can see mostly we could get chronic patients, but some have few months to some have several years of stroke. And we were trying to see whether we get any linkage between the looking pattern and the neurological disorder. So this one shows a very interesting output. So this is the left eye and this is the right eye coordinate. So the top figure to the top left. So if my both eyes are looking to the same point, then I should get a single dot. That means my both eyes are moving together and I'm exhibiting convergence properly. Here you can see the left one, the red dots indicate that my target is to the left. The blue indicate my target is to the right, to the center, and my green indicates my target to the right. So you can see a distinct pattern in the case of healthy participants. But for the post-stroke, you can see the dots are all over. That is, one eye is looking in another direction, the other eye is looking in some other direction. So there is a neurological disorder. So the eye can be used as an indicator of neurological disorder. So then we compared between the deviation in fixation between a point and the actual point, the fixation point and the actual point. And the dark black color shows of the stroke participants and the gray color shows of the healthy. So you can see in each case, whether it's horizontal or vertical movement, the stroke group exceeded the healthy group. And you can see a lot of deviation, the standard deviation is quite large. So we did not do any statistical analysis, but we are reporting the overall findings, the group average findings. And these are on the individual level, the figures to the bottom, which shows that they are quite heterogeneous. This is the overshoot. So you can see that whenever there is an object and I'm following the object, if I have a tendency to overshoot the target, that is move beyond the target, and that is what is overshoot, and something which is called as undershoot. So you can see that the participants were exhibiting a wide variation in the overshoots, Okay. Now, the normal blink rate generally is about 8 to 12 blinks per minute. You can see for all the participants, mostly some of the participants were showing dry eye, that is S1, S2, S3, S6. They were showing as dry eye effect, that means they were not blinking at all. And for certain participants, they were showing blinking, high blinking effect. So for few of the participants, we had MRI data and we could see that the S8, which is the highest blink rate, had issues with bilateral dystrophy, and that is where those patients indicate a high blink rate, and that was what we could find from the MRI reports as well. So the eye data was really giving good results, notwithstanding we don't do the MRI, which is quite costly and it's also not available at all places. This I have already discussed. And this is where the smooth pursuit. So you can see that even at the end of the 5-minute task, from the plots itself, you can make out whether the patient has any disorder and has any neurological disorder or not, and whether he's healthy. So that is, I complete the first portion of the talk. So the next portion is, you can stop me at any point if you want to have any discussions. So the other point is, so here I was showing that eye can be used as a predictor of neurological disorder. We also look at one's walking pattern, that is gait, how gait can be used to indicate neurological disorder. So this is motivated by the fact that different patients, like post-stroke patients, even elderly individuals, show abnormality in as far as mobility is concerned, and also regarding gait speed, and also the manner in which they walk. You will find that they will often exhibit weakness, because of which they cannot walk properly, in their weakness in their legs. And you will see that majority of the post-stroke patients have most of the weight bearing on the other side, that is on the non-paretic, that is the healthy side for hemiplegic post-stroke patients. And for the on the paretic side, they take less than half, 50% of the weight. So there is a tendency for them to fall, and also their gait, that is walking pattern, becomes abnormal. So literature shows that, in fact, there are very costly solutions where people use cameras and also like gait pressure mat, where they find out the pressure points of one's walking, and then they try to identify whether the person can walk properly or what are the gait parameters. Before I go to gait parameters, there's something called as stride step. If you are not aware of these terms, let me quickly tell you. So the stride length is the heel to heel touch. So right heel touching the ground. Again, the right heel comes back to the ground. That is the heel to heel touch of the same leg. That is the ipsilateral leg. That is what is the stride. The step will be for the opposite legs. That is the contralateral, left and right. And accordingly, if my feet is in contact with the ground, that is the stance, and if my feet is in above the ground, that is, say I'm walking with my right feet on the ground and my left feet is in the air, then that is called as the sweep face. So we thought that how about we provide the pressure sensors below one's feet in the shoe, and that is what is the thought behind why we went for an insole, an instrumented insole. So this is how it works. It's a wireless insole, and you can find out. So you can see the figures on the right side. We are picking up heel motion, toe motion, and other parts of the heel and other parts of the feet. And we're trying to find out when my heel is touching the ground and when my toe is taking off the ground. And that's how I find out gait events, which is stance, swing, stride time, stride length are also being computed from those parameters. So the figure at the bottom shows that it's a healthy participant. So you can see both the left and right heel are moving in a very similar fashion. So the blue and the red curve are very similarly placed. But in the bottom figure to the bottom right, you can see that the blue portion is a lot. So the blue portion is the left leg data and the red portion is the right leg data. So you can make out this participant is a right hemiplegic stroke patient where he's putting very less weight on his right side or leg, but more weight on the left side. So we sort of went ahead to calibrate the data. So this is sort of our shoes. On the figure you can see the shoes, it is a shoes and it's a data acquisition system, and we calibrated it against Vicon. So Vicon camera, you can see the figure to the left, and we provide markers. So when the participant is walking with our shoes, our instrumented insole, we are collecting the data from the camera, which is the standard measure nowadays in gait labs, and that starts from 35 lakhs and beyond. So these are very costly system. And we are trying to do an indigenous insole which can provide gait indices, very similar to that of the Vicon. So we started with a group of healthy and post-stroke patients. And you can see these are the calibration curves. You can see that the absolute error of stride time, stride length, step length are quite less. So the error is very less than almost equal to 1% of error maximum. And that we can do for each leg, left leg and right leg. So the dashed bar shows of our instrumented shoe insole, and the dotted bar shows the Vicon based output. So you can see all of the figures are very similar. Uh, the absolutely bottom two figures are for the post-stroke patients. So you can see that the overall average might look similar between the left and the right leg, but for post-stroke patients as well, our system was able to pick up the gait very accurately as that of standard paper-based setup. So here we used a paper-based setup. This is the shoe insole that we have come up with, and it's a smart insole that we have named. This is our brochure. So several companies are showing interest, and hopefully, so our insole is being tested out in civil hospital in Bangalore, and there are requests coming from Delhi and other places of Ahmedabad as well. This is mostly for patients. It provides characterization of gait, so you know whether the gait is improper, and if so, the person has stroke or not, or the person is showing abnormality in gait, he might have a tendency to fall. For clinicians, we do not need the tedious approach of clinicians accompanying the patients, and also there is no subjectivity, it's quantitative data. So just a glimpse of how our insole works. So I'll just share a small video.
Walking is a biomechanical process natural to human life, thus is taken for granted. It involves coordination of brain functions and the musculoskeletal system. One's walk may need monitoring and correction either to recover from an injury, trauma, or simply to achieve excellence.
So this is the smart insole, shoe insole, and this has a number of sensors impregnated in the shoe to quantify the manner in which one walks. So this came up as a part of a bigger research project that ranks shoe can record various spatiotemporal gait parameters such as stride time, step time. Even it can find out gait stability ratio, which can prevent falls, which is an indicator of falls, and also the symmetry, the way in which we are using both the legs.
Install helps in recording data in an autonomous manner and analyzing the same with a computer program to understand improvements in various aspects of walking, helping healthcare professionals to determine the course of treatment.
We have used different technology-based solutions.
Stable enough over a long time and also accurately communicating over a long range.
The calibrated sensors are used to acquire data perfectly. A proper care has been taken for their placement on the design insole.
The design team got involved in the project once the technology was tried and tested. We analyzed various configurations for products so that it becomes usable without affecting the technological performance. In the end, we've achieved a sole that can be removed from one shoe and can be put in any other shoe. In the end, we've tried to push the product towards a very user-friendly, aesthetically attractive, and acceptable in the market.
Using the least amount of area for electronic components, and by just adding the necessary elements to it, we have maintained a good composition of simple and compact design. The texture, color, and could visualize and record the shoe data. Later, it calculates gait indices from the recorded data for rehabilitation and clinical purposes.
So the gait-related indices can be monitored and also recorded in computers, in laptops, wirelessly. And as a result, it can contribute to telemonitoring. In fact, this can keep an eye on how a person is walking and what is the rehabilitation outcomes. Also, there can be different applications, like it can be used in gyms, it can be used in rehab centers, old age homes, so it has a number of diverse applications.
Install can potentially change the diagnostic scenario for walking parameters. IRACS at IIT Gandhinagar is working on more technologies that will address not just biomechanical issues but cognitive issues as well.
So this is where I was presenting the install, and one of my colleagues, Professor Manasi, is looking after the design portion, and she was also presenting. So I started. This was me who was starting to speak on the install. So this is how it works. Um, so again, stop me at any point if you feel you have any questions. Now, the last portion of my talk is another 20 minutes or so. I'll take. So the virtual reality based rehabilitation platform for patients with neurological disorders. So far we have told that okay, the patients have issues with eye. Are we able to track it? Yes, we can. The patients have issues with gait. Are we able to use it for a diagnostic purpose? Yes, we can. Okay, then once we have detected that they have issues, how about we can rehabilitate them? So that is where here I am presenting mostly the balance, though I also work on the gait. Um, so there so you will find that mostly post-stroke patients aged below 50 years, that is also a large number, and many, very, very few of them, it's hardly 7%, receive rehabilitation. So below 50, they are in a working stage, working age, and so the socio-economic status is very adversely affected. So we need to do something with them. And you will find mostly they have issues with balance even before leaving the hospital, because it's very difficult to afford to stay back at the hospital for a long duration. So they need rehab. You will find that mostly the patients, if they say we are stooping forward, putting our feet at one place, and we are stooping forward to take a bottle to drink some water. So in that case, we have to displace our body weight without moving the feet. And if we are not properly balanced in displacing our body weight, that is the center of pressure, then obviously we will fall. And that is where our idea was, how about we develop games, virtual reality based games, where people can play and interact with the games and sort of improve their balance. So mostly we were working on the postural stability and balance, which in fact, if this reduces, then it has a very bad effect on their confidence. They cannot move outside their houses. They always need someone to accompany them because they are less confident and they are prone to falls. So let's first see what is the existing infrastructure, what is the existing options are available. So conventionally, we'll find that the therapists use walkers and ask the patient to walk or to balance. Even for step tasks, they use a parallel bar and they see the static and the dynamic balance because they have a risk of falling. So they use, there's always therapists standing along with them. In fact, sometimes they have to literally help to move their feet even. So, but these exercises are very repetitive and monotonous. And you will find that when I went to civil hospital, I was hearing that the patients are not coming because they are tired and bored with the rehab. And that's very common. But when we set up our setup at one of the hospital rooms for about 2 months, we could see patients waiting for us. And my students used to tell that the patients are waiting to play the game. And at the end of the 2 months, we could see patients who are coming with their sons, bringing them along with them, their child, to bringing them, holding them to the hospital. They were walking with their own stick and with their own feet. So we could see a lot of change in the process of rehabilitation. So we were planning to make a clinically valid home-based tool which can reach to every household, whether it's an urban or rural setting, and it should be a very simple setting, but technologically very intensive. So this is the setup. So we have a V-Balance board, which is used in games. And we designed a virtual reality-based stimulus, which can be projected onto a computer. So you can see that the patient stands on the board, and we compute his or her center of pressure, and then accordingly move the virtual object like the car at the center, the virtual object, dynamically in the environment. And that is the task. So we offer different difficulty levels. I'll give a small video of how the task is. And based on how much you have to displace, either you have to displace your body weight less or your body weight more, or you have to do cumbersome tasks, quite demanding tasks. Um, so these are the stimulus which we offered. So the central hold is the one which is written. That is where the patient's initial center of pressure will lie. And then the target is given and the participant will be asked to stoop in different directions in the direction of the target. And there are tasks of different difficulty levels. So this is a state machine representation and AI based, though all of the tasks have the inherent AI engines involved, even in the previous research studies that I have presented. Here I try to give plan to give a state machine representation where I compute one's performance. So the performance can be in different facets. It can be how I take my weight forward, or how long I stand in my displaced position, or whether I'm taking my ankle off my feet, and that is what is ankle strategy. Then I negate marks, that is I penalize them. So different matrices decide my performance, and if my performance is good, then only I raise them to a higher difficulty level. So this is a short video of the task. So you can see the subject is standing on the balance board and the computer is there. And the person is bending forward, and so immediately the center of pressure moves. So this is of one of the difficulty levels. So we have done in 5 different directions.
Well done. You are doing great.
So we give feedback as well. And it can be like a maze. So you have to just balance your weight so as to arrive at these intermediate goal points. It's a quite difficult task, but the patients could do. And it's timed. So this is another difficulty level.
You are doing great.
Otherwise, the system will give the same task again, but with a different template. So this task is a final difficulty level where the ball has to be taken from bottom right to top left, or bottom left to top right. And we see the difference in the timing.
Well done. You are doing great.
So this is a very small snapshot of the task which we designed. It's a long 20-minute task. We enrolled almost 7 post-stroke and healthy participants. And you can see that over multiple exposures, there is an improvement both for the healthy and the stroke group. Obviously, we could see healthy group was mostly performing 80% on a minimum, but the stroke group minimum was barely 60%, but still they improved for all the difficulty levels. Not only they improved, they could do the tasks faster. So the time for execution reduced for both the healthy and the stroke groups. Also, the difference in the interval of time, that means how well balanced my both left and right legs are, that also reduced considerably for the post-stroke patients. So the figure to the right shows for the stroke group, the time difference reduced. So they're inferring that there is an improvement in the balance. So you can see that this is for the healthy and stroke. For the circles show stroke and healthy are the triangles. So you can see that for the healthy, mostly they are at the 4th difficulty level. So they are quite good in their balance. But for the stroke group, you can see mostly they are hovering in difficulty level 1, 2. Then they go to difficulty level 3 and few go to difficulty level 4. So this we wanted to say that we wanted to see whether they are doing well in their virtual environment. What if how they are doing in the real world, how they are actually performing on the balance board. So the figure to the left shows that their center of pressure was fluctuating all over the place, and figure to the right shows the center of gravity or the center of pressure was much less fluctuating, and it was much more controlled. A brief on the different types of studies, tasks we do before I end. We also have a one-touch doctor, which provides on near-infrared spectroscopy based detection of different physiological parameters. And again, we are finding at least two different big industries are showing their interest to take over this license. I also work with Parkinson patients, and this is example, the figure to the right shows a Parkinson stick, which can detect one's freezing of gait. Again, we have applied for the patent for this particular solution. And I hope that by next another 2.5 years, we will be able to, me and my students will be able to come over with a smart walking aids system for the Parkinson patients. And I also work with in the area of stroke and autism. So I was telling that I work with affective computing in the area of affective computing. You can see different types of systems are here. So I'll not go into details. If you are interested, we can speak. These are the funding agencies, which is DST Tide, Indo-French. So I have done quite a lot of international projects, India, France, and India, Singapore projects, BIDUC projects, and also SORB. SORB is, but this is an Indo-US project which I'm working, and also of course on the cognitive science project also I did, added to other projects. These are the list of references. Thank you. So, and I'm now open to questions. I tried to complete within 2:15, but it took 2:17, so that we are open for questions. Thank you.
Good afternoon, ma'am.
Good afternoon.
Ma'am, I have a query on EOG-based system.
Yes.
In one of my experiment was just teaching to the student, I was recording EOG signal. In this, I used a surface electrode to be placed on the face and the overhead to record the horizontal and vertical motion. Right. But in the same thing, I was also modified that with the gaze experiment, I also try to go with the gaze position, that what will be the effect on EOG.
Right.
So with the help of a 3 electrode, I recorded a single EOG channel, which is a combination of horizontal and vertical signal.
Very nice.
Right now. But the major difficulty I felt over there is to segregate between the horizontal and vertical motion from the single channel EOG signal.
Yes.
So, ma'am, what is the possibility here so that we can segregate the signal here?
Right. So I will tell you so in fact, so whenever you are doing the horizontal, it most often happens that the lateral and the medial muscles of the eyes are actually becoming active, and that is where you are doing the horizontal, and the inferior and the superior muscles are actually becoming active for the top bottom, that is the vertical movement. Vertical motion.
Yes.
But you will often find that whenever someone is moving the horizontal, making a horizontal movement, the vertical is also affected, because there is also something called as torsion, where the eye actually rotates about. So these are like very often linked to each other. And so it is very often possible that your horizontal movement which you are telling, actually there is some vertical movement as well. Right. So the best way to overcome that is, instead of using a single channel, I would tell you to go ahead with the double channel, at least a double channel, where you can put for the horizontal and the vertical movement two channels, at least two channels for the EOG measurement. And did you use a ground for the ear? Did you use any ground?
Yes, ma'am. For both the channel, I have used the ground. For the single channel recording, again, I have taken one point as a ground reference point.
Okay, okay, okay. So I will suggest that better you use two channels because it is so my research findings show that it is very difficult to distinguish even if you go for the frequency domain representation. Distinguishing between the horizontal and the vertical movement is difficult for the healthy persons. But if you consider patients with say cognitive impairment, which I am also in one of my studies, where I can see the vertical becomes more adversely affected than the horizontal. And in that case, you can distinguish the vertical from the horizontal very well.
Okay, right, ma'am.
So I would
Thank you,
suggest
ma'am.
you go
Thank you for
for
the
the
suggestion.
double channel. But very nice question.
Yeah, thank you, ma'am. Thank you for the suggestion.
Thank
Ma'am, can I ask
you.
one
Yes, please.
question?
Yes, please.
Ma'am, actually in EEG, except 1020 system, suppose if we want to predict something, so can we use only 3 lead or 2 lead or maybe 4 lead that particular specific point if you know, suppose to find out the epileptic seizure, or suppose I want to find out another kind of disease, somehow apnea can be also find out from EEG. But
Yes.
you know that we don't have that much of instrument that we can use 1020 system that cost is near about 7 to 8 lakhs.
Yes,
So
yes,
we
yes.
can design ourselves that will be only 2 or 3 lead. So is it possible? So it will be
So
helpful for us.
right, right, right. It's a very good question. So, say if you are more interested to see the eye movement, say for example, you can use the occipital. So that C3, C4, CZ, you can do this occipital. But if you are interested, then three sensors will work. But if you are interested to find out the eye related, say, problems, then you have to do the frontal eye field and the frontoparietal dorsolateral, so the DPLFC, prefrontal cortex. There you will need at least 4 to 5 electrodes. And if you want to find out, say, for specific stroke cases, then you can use mostly the motor cortex. The motor cortex, the one at the top. So maybe I'll just switch on my video so that it is easy. So it is like at this portion. So one and one at the
Yes.
top. So that is the portion where you can put, or you can put at the prefrontal and the frontal zone. You can put. Um, uh, that is where you can put your sort of
The
electrodes.
electrode.
But for say apnea, sleep apnea, and say for this detection, epilepsy detection, I am bit doubtful on this 2 to 3 electrode thing. So in fact, I am using one electrode, one EEG set. I've just started using it, and it's 8. So 8 to 7 to 8 is, I think so,
7.
that is 7 to 8. At least you should have. Though people say 16 would be a very good configuration.
Okay, ma'am. So in future, actually, I won't work about the EEG. I have developed the system EEG and working for the research purpose myself and apnea purpose and
Very
also for
nice.
pulse. But EEG system actually that fear came to me that 1020 system I cannot generate. I cannot develop that type of system. So if it's possible 4 5 lead, so we'll try in our lab to develop that system by ourselves. Actually, you know,
Right.
in private institution, it is very difficult to
I
purchase
know.
one good instrument.
I know.
This is one of the difficulty for us. We normally develop the
Right.
system ourselves and then we do our work.
Right, right. It's a very, and that is through to solely the in-house, everything built in-house, calibrating. It's a very tough, I know. But how about that? There are many summer internship options offered. So maybe you can send some of your students to my lab in the summer, and we can speak. And if possible, since all of us are within Gujarat, I don't feel there will be much trouble if you are within
Mm,
Gujarat.
Okay, ma'am. Then if it is possible, next we'll come and I will contact with you.
Right,
And
right. Let's
after this
see.
pandemic situation, if possible, definitely few of students
Yes,
from this was Engineering College in
right.
Kolkata, they will go in your lab.
Very nice.
It will be very helpful for us.
Yeah,
But
sure,
after
sure.
this pandemic,
Because after
very
this,
very thank
about this COVID.
after this COVID, ma'am.
I
And
know.
definitely we'll send, and it will be very
Yes,
helpful for us.
very
Thank you,
nice.
ma'am,
Yeah, of
uh,
course, of course, of
for your
course.
suggestion.
Hello, madam. May I ask you a
Thank you, ma'am.
small question?
Yes, yes, please.
Yeah, madam. This is Jeet Banerjee from Adamas University, Kolkata. Madam,
Okay.
I was observing your presentation and I came with a new idea that if you have heard about flat in small children or in matured people as well, it is an
Pardon me,
orthopedic condition.
your word broke in between.
Okay, I was talking about flat foot, a medical
Yeah,
condition
yeah,
that is
yeah, yeah.
prevailing in.
Yes, yes, yes,
So
yes.
I think using your methodology, we can also have some
Yes,
solutions for children or people suffering from flat foot. Is
absolutely,
it
absolutely. Absolutely, you are absolutely right. So there are two types of flat foot. One is your heel first touches the ground, and in fact, and very minor time difference the toe touches. And sometimes the flat foot is the other way around, which is sort of a foot drop, where the heel touches, toe touches first, and then the heel. So both cases our shoe can detect. A very good question. It can very well do.
yeah? I and my students would like to investigate this with your guidance. If you can
Of
kindly
course,
share
of
your
course.
email ID.
Of course, my email ID is uttamalahiri @iitgn.ac.in. UTTAMALAHIRI
Um,
@iitgn.ac.in.
okay. Can I find your profile on the website of IIT Gandhinagar?
Yes,
Then it
yes,
will help.
absolutely, absolutely. IIT Gandhinagar,
Okay.
electrical
I'll
engineering.
get.
Really
Okay.
nice,
Okay.
Banerjee, to speak to you. Yes, we will work.
Okay.
Hello, ma'am.
Yes, yes, dear.
Yeah, I have a question related to the gait.
Yes,
Uh, you discussed about gait for the stroke patients,
yes.
and also you talked about the Parkinson patient. There is a difference between the gait parameters
Yes,
for the stroke patient as well as Parkinson patient.
yes, very well pointed
Yes,
out.
yes. So how do you differentiate? The Parkinson patient will, move forward when they walk. Will, will your insole system will it detect that also?
Yes, yes, very good question. Very good question, Professor. So ours is we are applying the shoes to Parkinson patients, where we are more interested in parameters like cadence, double limb support time, step time step time and stride time. Not much in the other parameters. Like single support time is also there. We are not so much interested with the single support time, but more into the double limb support time, because when they tend to freeze, they tend to stick their foot to the ground, and that is where both the feet is in contact with the ground. And this double limb support we are able to pick up, which I have not reported in this presentation today. We have been able to pick up with a very high level of accuracy the double limb support. And another thing which we are trying to do is, as per literature, at least 6 steps before, sorry about that, uh, at least 6 steps before the actual freezing occurs, which is the sticking of the feet to the ground. I hope you already know it. There is a symptom that the person is about to freeze, so as per literature. So we are trying to pick up the symptom in as less as 2 to 3 steps. And every 2 to 3 steps, we are trying to see different parameters and we are trying to pick up the possibility of once freezing. And that is where these gate features we are looking. And then we are going forward in addressing the freezing as well.
Okay. Okay. But the stick which you talked about, the smart stick which
Yes,
you are
yes.
talking about for the Parkinson patient, so it's going to be a rehabilitation kind of work, right?
Yes, it's a rehabilitation work, and where in fact we are sort of picking up for the stick. It's a different algorithm altogether. So for the stick, what we are trying to see, if a person with Parkinson is walking with the stick, the way he puts the stick on the ground above the ground is different. We are actually picking up that the profile, the stick movement profile. And from there, we are trying to predict the possibility of once freezing. And then we are giving them different types of cues, like external cues, which are automatically triggered based on whether my possibility of freezing of gait is being detected. So that is what we are doing in the stick. And we have tried out in patients with even patients who are like lying on the bed. And the caregivers actually help them to stand up. And we have given them our setup. And they were down to tears because they could walk. So literally it helps a lot. It is absolutely a rehab based study. You are
Okay.
absolutely right.
Yeah. Thank you. Thank you. All the best for your.
Thank you. So the entire video, some portions of the video actually I was cutting. I hope you have understood. I was like literally cutting some portions because those are portions because this will be recorded. So I was sort of taking out portions. But if you are interested, we can speak at length, and we have papers published as well, and we can distribute, and we can go ahead accordingly. So if you are
Yes,
interested.
ma'am. We would love to. We will
Yes, of
take it
course.
up in a later stage.
Yes, we'll love to collaborate.
Yes. Thank you, ma'am.
Any more questions? So, are there any more questions?
Hello.
Yes, hello.
I think no questions are there.
Okay.
So I ask participant if you have any questions you can ask. Otherwise, uh, we will end this session.
And I think so, Mr. Bala, if my email ID can be given to the participants, and in turn, in fact, I will learn many things from them. There are participants who know much more than me in some of the areas, and some of the areas I can also complement. So I would love to interact with them and carry the collaboration forward. So
Definitely,
if you
definitely,
can share,
definitely.
yes.
I will
Okay.
make that ready.
Good afternoon, Professor. Good afternoon, Madam.
Yes, good
My name is
afternoon.
my name is Dr. Anandi Ramachandran. I
Yes,
am
yes.
working in Delhi in International Institute of Health Management Research, where I
Wow,
am working in
nice.
the area where I am working in the area of healthcare information technology. In fact, most of the sessions of this workshop for me is really new because I am not from more technological side.
Okay.
So I'm more into from management side and general healthcare information technology. But your session was really interesting, in fact. So it's
Thank you.
as you said, I will definitely get back to you because there's a lot of things which I need to clear my doubts because I'm a novice. In fact,
Oh,
I will take
no,
your
no
guidance.
issues.
I take your guidance. My area was actually using technology in healthcare in the public health, especially
Oh,
for the community. So
very nice.
while we were speaking, there were a lot of thoughts going on. So I
Very
hope you
nice.
wouldn't mind
No,
me
no, no, no,
asking
no, no.
you. Yeah,
In fact, I will
thank
learn
you.
a lot from you as well. So I would
Yeah.
love to collaborate.
Yeah, I'm more into community interaction, and so I'm right now I'm working on certain projects which is related to mobile based infectious disease surveillance, and yeah, so areas like that. So I will definitely, I'll get back to you. It's an interesting area though. I think so I should start venturing out into this with your help.
Mostly I work in the area of wearables, like wearables,
Yeah,
virtual
because
reality.
that is what it was giving me an idea, because I had also published some paper